Good. So here, okay. Hello everyone. Thank you, Nico, for giving me this opportunity to talk to the students. South Africa, I was there last year, and I really enjoyed the interaction with very enthusiastic South African students. So today I'm going to talk about, I would like to introduce some key concepts of nuclear physics, which might be useful for many of the students and in their research projects, and also for tackling problems in nuclear physics. So the structure of my talk is, so there's three parts. So first I'm going to introduce the notion of the two-centigrade model. I'm going to define diabatic and diabatic states. And then I will illustrate an application of these concepts in describing fusion of heavy nuclei, and to address the effects of called the diabaticity. So it was connected with the diabatic single particle motion. Finally, I summarize and give some perspective of this of application of these concepts to nuclear physics phenomena. So the idea of the two-centigrade model is old, relatively old, so as old as me, so 50 years old, more or less. So the two-centigrade model is a basic microscopic approach to describing the single particle motion in low energy heavy ion collisions. So in fact, this is a legacy of the Frankfurt School of Theoretical Nuclear Physics, led by Professor Walter Greiner. So the concept was introduced in practice in heavy ion physics at the late 60s, and it was so by the work by Holzer, Mosul, Greiner, and at that time the concept was applied to fission, to understand microscopically the origin of the asymmetric fission yields and due to shell effects. Because before that, the description was mainly based on liquid drop ideas. So Strutinsky introduced a great idea of extracting from single particle spectra what is called shell corrections to the macroscopic collective energies. And it allowed to calculate binding energy, potential energy surfaces. And it was very useful for addressing fission phenomena. And here I just show some key works in the field of the two-centigrade model over almost 50 years. There are other works by other researchers, but here I would like to highlight so the very beginning of in this field, most of the two-centigrade models were based on phenomenological harmonic oscillator potentials. And later in the 70s, the concept was extended to more realistic finite depth potentials, like the phenomenological Wu-Saxon potentials, and also was extended to application not only to fission, but also to heavy ion reactions, fusion, cluster decay, cluster radioactivity, alpha decay. And 20 years ago, when I came to Germany for my PhD with Professor Werner Scheidt, who was a student of Walter Greiner, I learned about this concept and applied this concept to understand the fusion of heavy ion leading to super heavy elements. At that moment, I applied the adiabatic and diabatic two-centigrade model. I will explain next what those concepts to understand the fusion pathways, because it's not clear how heavy nuclei fused once two colliding nuclei reach touching configurations, how this dinuclear system evolves into the compound nucleus. And later on, I developed the two-centigrade model with realistic deformed Wu-Saxon potentials using very powerful techniques, which is called potential separable expansion methods, which allows us to know single particle states of nucleons moving in a two-center mean fields, phenomenological mean fields. And this is an example of here of a two-centigrade model with Wu-Saxon potential, realistic Wu-Saxon potential. In this figure here, you can see on the y-axis cuts of the two-center potentials. This is x equal to 0, y equal to 0. This is cut along the z-axis, and capital R denotes the internuclear distance. So here you can see different configurations of two colliding nuclei. These configurations correspond to equipotential surfaces in this two-center mean field, phenomenological mean fields. In this case, at the bottom panel is when the distance between the center of mass of these two shapes is about 16 femtometers. And then you can see what happens when this distance decreases. You can see that these two-center Wu-Saxons, this is, for example, for neutrons, merges into and form a single container, which is a single Wu-Saxon for an spherical compound nucleus. So you can imagine that this is actually a eigenvalue, eigenvector problem. So we need to calculate the single particle energies. We need to diagonalize the Hamiltonian matrix using certain bases. So you can imagine, for example, using a harmonic oscillator basis centered around each mean field potentials. We can calculate a matrix, Hamiltonian matrix, and diagonalize this matrix. And then for a fixed internuclear distance, we can see what are the single particle orbits. Here, for example, this is the example, the collision of an oxygen 16 and a calcium 14. These are two spherical nuclei, so we use two spherical Wu-Saxon potentials. We fix the distance and we diagonalize the matrix. And you can see there are different orbits. And these orbits, when the distance is very large, just these two orbits, there are orbits that belong to the oxygen 16. There are other states that belong to the calcium 14. Here, this is a typical spectroscopic representation of those states. So S, P, D, S correspond to orbits with different orbital angular momentum, L. And this 1/2, 3/2, etc. are a value of a total angular momentum. Those quantum numbers are good when the distance between the Wu-Saxon potential is large, but when the Wu-Saxon potential come together, these states mixed, and the only survival quantum number is what's called omega, which is a projection of the total angular momentum onto the internuclear axis. So when you can see when R is relatively small, 6 femtometers, you see a lot of mixing, and then as a result, asymptotically degenerated states in the magnetic quantum numbers decouples. And you can see here, and so behind this picture is the assumption that the time scale associated with the motion of a capital R is much larger. Typically in collisions at energy near the Coulomb area, this time scale is of the order of septoseconds. It's 10 minus 21 seconds. Is much larger than the time scale associated with the motion of a nucleon in the volume of the system. So this time scale is at least 10 order of magnitude shorter. So 10 minus 22 seconds. So for each configurations of the two central potentials, the nucleons have time to readjust their orbits to the mean field. So here in this diagram, which is called single particle correlation diagrams, you can see a body crossings of levels with the same quantum numbers omega. These are molecular, these levels are called molecular single particle levels, and these are the body crossings level with different quantum number omega they can cross. So this is a result of the quantum mechanical solution of the eigenvalue eigenvector problem. Okay, associated with this value of the energies, these are energies, which are eigenvalues. They are eigenvector, which are the wave functions associated with those energy levels. No? And there is a computer code available for the public, which has been recently published in Computer Physics Communication. So this code may be useful for calculating states, two-center states for a spherical Woos action, and this may be useful for applications. So here you can see the notion of a two-centered model using two harmonic oscillators. So instead of bringing together two Saxon mean field potentials, we can work out a problem with two harmonic oscillators. This is the work done in Frankfurt in the 70s, early 70s. And here you can see an equipotential shape in these two-center mean fields, and there are typically 5 collective coordinates associated with this problem. One is the lambda, which is describe the length of the system or the internuclear distance between the two fragments. So the fragments are those two parts of the system, which are when we divide the system through this dashed line here, which is called, this region is called neck. And associated with this, there is a neck parameter, which is here defined as a ratio of two value of energies. Epsilon prime is the, you can see this is the, if we intersect the two parabolas, the two harmonic oscillator, there is an intersection value of the energy. And the other value has associated with an extrapolation in the region between the two centers of the harmonic oscillator. You can imagine that we can interpolate the two harmonic oscillators smoothly using a polynomial function, and the ratio between these two values of energies is defined as epsilon. And here on this part you can see a family of nuclear shapes as a function epsilon, which is associated with the neck. You can see as epsilon increasing, we have a neck with a small radius. And as epsilon decreases, the neck value or the radius of the neck increases. And here we see in this axis, we see lambda, which is associated with the length of the system normalized with the diameter of an spherical compound nucleus with the same volume that the volume of this, because all these nuclear shapes here have the same volume. Because of the incompressibility of the nuclear matter, it is assumed that the volume of the system remains constant. So here, and other coordinates, collective coordinates in this model is the deformation of the fragments, which are defined by the ratio of this semi-axis, A2, for example, B2 divided by A2, these two semi-axes define a beta, which is a deformation parameters. And another one is the asymmetry, the mass asymmetry, for example, or volume asymmetry, is a parameter that describes how different in mass are these two fragments. Okay, so here I show you in these cartoons the adiabatic picture of fusion. Adiabatic means that the two nuclei melt together as two liquid drops, and essentially the formation of the compound nucleus happens by melting these two liquid drops, and the motion is along the lambda or elongation degrees of freedom. And here at the bottom you can see a potential, collective potential energy surface as a function of lambda elongations and the neck parameter or neck coordinates. As I mentioned before, these configurations of two touching nuclei will be here sitting in this position. And when lambda is large, it means the two fragments are separated. and epsilon is large, let's say epsilon is equal 1, we are here in this slope here of the potential energy surface. Here you see there is a barrier. This is a typical Coulomb barrier, and once the two nuclei start overlapping, then we are in this region here of this map of contour map of energy. These energies are binding energies of the whole system, and you can see here trajectories. And these trajectories correspond to classical calculations of how these two touching nuclei moves along this landscape. So in this calculation, which are published in this paper, the author solved classical Newton equations using irrotational mass parameters, which is a mass tensor, for the kinetic energy of this motion, and also they use friction. So they assume there is a Rayleigh type of friction, and they calculate with initial condition that the system is here, sitting on this top of this hill. The system will move down toward the valley of the compound shapes, of the spherical shape, which will be here in this configuration. So there is a problem with this picture for describing fusion, because if we calculate here on the left, you see the potential energy as a function of lambda for different combination of projectile and targets, and this crosses here denotes the touching configuration for this different fragmentation of fermion 246. So if initially the system here are allocating this, you can see that it's basically the system will run down towards the small lambda values, and this compound nucleus will be formed. If we calculate, of this author calculated the probability for compound nuclear formations as a function of the initial location of this dinuclear system, it's called lambda v. This is where this crosses, if this crosses here or here or here, and calculate what is the final probability for compound nuclear formations as a function of this initial condition. They obtain this line here. No, this is a solid line for palladium on xenon and so on. And here you can see experimental or associated with interpretation of experimental data of value of these probabilities. You can see that the calculated values are much larger and disagree with experimental extracted values, and also the isotopic dependence is different. So you can see that for example, palladium plus xenon has a very, very small probability, and here in the calculation is very large. And so this theoretical picture contradicts observations. And how can we repair this situation? Well, one possibility is to think that this adiabatic motion of the particles is not fully true. So here in this schematic picture, I show you the energy, and this is the y-axis is energy, the x-axis is collective coordinate. This q value can be thought of the distance between the two atomic nuclei, between the center of mass of the nuclei, and these adiabatic levels are the levels that result from the diagonalization of a single particle Hamiltonian. As I show in one of my figures, there are avoided crossings for levels with the same symmetries, the same quantum numbers, omega. Well, around these two levels, the nucleus, if the coordinate q, in this case, or capital R, is the velocity associated with that coordinate is relatively large, this nucleus will not follow these adiabatic levels, so the levels of the smallest energy, but they can follow the so-called diabatic levels. So diabatic levels are you can visualize in the sense of replacing these avoided crossings by real crossings, and quantitatively these levels can be calculated. So here in this figure I show energy of neutron energies as a function of the internuclear distance. And on the left-hand side, you see adiabatic states. This is for omega equal 1/2. This is just a set of levels with the same symmetries. And these levels are obtained by analyzing this two-centered Hamiltonian matrix. And if we calculate the so-called radial non-adiabatic couplings, all the couplings between two states, alpha and beta, for example, 3 and 4, or 5 and 6, or 7 and 8, etc. And this operator here is related to the kinetic energy operator for the internuclear motion. And R, as I said, is the distance between the center of mass of the two nuclei. And here on the left-hand side, I show the absolute value of these radial couplings. And you can see that they are pronounced structures of these couplings when a body crossings between the levels exist. For example, if we look at the coupling between levels 3 and 4, level 3, the solid line, we see that at distances other than the distance where this body crossings appears, this coupling is very small, but at the location of this body crossings, the couplings are very strong. And one possibility is to diagonalize this coupling matrix. And after this diagonalization, this is a change of basis. We can replace this body crossings by real crossings. And this new basis is the so-called diabatic basis. And instead, if you can imagine, if a nucleon is in level 3, when R decreases, the nucleon will remain in this level 3. But if the nucleons moved in a diabatic basis, then the nucleon will goes up in energy, and it has tremendous consequences on the features of the collective potential energy surfaces, and as a result on the collective motion of the system. So next, I like to discuss the effect of this diabatic motion on fusion of heavy nuclei. The two key messages I like to convey is that this diabatic effect, or diabatic single particle motion, hinders the motion of the nuclei to small distances, and also hinders the growing of the neck between the two in the dinuclear system. And as you can imagine, as the nucleons follow these diabatic levels, there will be an extra of energy gain into the system because of the occupation numbers of the level changes. So as a result, these contributions, called diabatic contributions, increases as lambda decreases. And this here you can see for molybdenum on molybdenum, the contribution for neutron and protons, and you can see there's a huge amount of energy gains if nucleons follow diabatic orbits. And as a consequence, the total potentials, binding energy as a function of lambda of the system will increases. So this is the total energy, including this diabatic contribution. So this diabatic motion produces a very repulsive core in the nucleus potential. As a result, a dinuclear system will be formed, and near the touching configurations, and this dinuclear system will live for a certain time at these very shallow pockets here of the nucleus potential. So there are other lines here in this figure I don't want to discuss because of time. So here I show you what happens in the neck coordinates. So as I said, when epsilon is large, the radius of the neck is small, and the lambda equal 1.56 is an elongation which is close to the touching configuration between the two palladium nuclei. So the value of epsilon about 0.8, 0.7 here, and this minimum of the energy is the optimal value for the energy of this dinuclear system. And if lambda decreases, for some reason. Then we see also that the value of the energy is very flat relative to epsilon. So, and we interpret the motion in epsilon is just a derivative of this potential as a function of epsilon. The force would be basically zero. So it allows us to conclude that the motion in epsilon is also very, very constrained, and the system doesn't evolve much to large value of the neck radius. And here I show you the concept of dynamical collective potential energy surface, because the diabatic motion produces excitation in the single particle world. So as a consequence of the diabatic motion, many particles, many holes in the spectra of the dinuclear system is formed. So there will be an excited dinuclear system, and this dinuclear system cannot move towards small lambda values because of this repulsive interaction potential here. But of course, there is some residual interactions that allows the depopulation or change of occupation numbers of these states. And as a result, this repulsive core decreases in time, and this release of energy, of collective energy, goes into heat into the system. The system heats up, and there is at the same time the system, of course, evolving other collective variables. But this internal barrier is a function of time. So this collective potential energy landscape is time dependent. And here you can see what happened with this internal barrier in lambda as a function of time. This is in septoseconds time scale. So here you can see 5, 6, 7, 8, 10 septoseconds. And this is when the entrance channel is palladium plus palladium. You can see how this internal barrier at the small lambda values decreases because of a relaxation and heating up of the system. This is what happened when the entrance channel is chromium and erbium. And these barriers are very large. So these final values here is what happens when essentially no probability exists any longer at the pocket of the nucleus-nucleus interaction. So either the dinuclear system has decayed, or the system has fused. So when I say has fused, means that the compound nucleus, a spherical compound nucleus, has been formed. And it is interesting to see not only what happened in lambda in the elongation, but also what happened in the another collective degrees of freedom, which is mass asymmetry. As I said, this is the coordinate mass asymmetry, and this coordinate is defined by the difference of masses of the two fragments forming the dinuclear system divided by the total mass of the system. So when lambda, eta is equal to 0, means A1 is equal to A2. We have a symmetric partition of mass. When eta is equal to 1, means the system has fused. So the whole mass is A1 becomes the sum of A1 plus A2. And it is here I show you the potential energy as a function of eta. So this dashed line is the value of the potential within the liquid drop energy, liquid drop picture. And we add the shell corrections, means the effect of the fact that the particles in the system occupies discrete levels, quantum levels, then we see this solid line. So, but you can see that when its internal barrier decreases in time, also the system has possibility of moving along the eta degrees of freedom. If a system overcomes this barrier here in eta, so that the configuration has a large value of eta, the system has fused. So here I illustrate two fusion pathways: fusion along lambda, if a system reaches small lambda values, and fusion along a mass asymmetry coordinate if the mass asymmetry is very large, beyond this barrier here. This barrier is called Bucinaro-Gallon point, which is a instability point in this or satellite point in this multidimensional collective potential energy surfaces. And as a result of this diabatic motion, I talked to you about two competing fusion pathways of evolution of a dinuclear system from this touching configuration to the anespherical compound nucleus. The system can go through lambda values elongation, like two melting liquid drops, or the system can exchange mass, and the bigger fragment can somehow eat the little one. And from this study, using this phenomenological adiabatic and diabatic potential energy two-centigrade models, I learned that it seems that these fusion pathways along the mass asymmetry coordinates operates with larger probability and than the fusion pathways along the lambda degrees of freedom. Thank you.
Alexis. So time for quick questions. So any question on the talk? Students are encouraged. We are late, but I can take one if you have. I see on the camera Emanuele Verdacci. Please go ahead.
Shall I stop sharing my screen?
Yes, please.
Yeah. Okay. Yeah.
You are mute.
Oh.
No.
Okay. Yeah, because the setup for the microphone changes often. No, I like this presentation and also the way in which you arrive to the conclusions. But what is really a little bit strange for me to understand is what is the time scale of this process, because the assumption is that you have fusion occurs because you have one proton or one nucleon absorption at a time. It's like a kind of a multi-step process. But now the fusion process should have some time scale. These two systems, these two possibility, the fusing of two liquid drops and the fusing of a nucleon one at a time should have a completely different time scale. For me, it's very difficult to put this in a picture where the time scale of fusion can be something like 10 to the minus 20, 10 to the minus 21 seconds. Mm-hmm. So I mean, this picture for me is a little bit odd to figure out, because these two ways should have a completely different time scale. So I don't know how an adiabatic fusion method can be compatible with the time scale of the fusion process.
May I answer your question?
Yes.
Yeah. So in fusion of heavy nuclei, the process which drives dynamics is quasi-fission. Quasi-fission is a premature separation of the nuclei from the dinuclear system. No? So these two pathways I have discussed compete with each other, and they coexist with quasi-fission. So what we have is a dinuclear system forms a nuclear molecule when the two nuclei are close as almost a touching configuration. But inside, for overlapping nuclei, there is a multidimensional space of variables. In this, I have focused on two variables. One is the elongation of a system, which is a nuclear system, and another variables is it has to do with the exchange of proton and neutron between these two fragments. It's the motion along the mass asymmetry or charge asymmetry coordinates. So the time scale is mostly determined by quasi-fission. This is some few of septoseconds. So I'm talking about time scale of the order 10 minus 21 seconds. And what happened for fusion to occur is that there is probability flowing along eta and along lambda. And at the same time, there is the decay of these dinuclear shapes. So as I said, the decay, shortest time scale is for quasi fission, which is the main process that hinders the formation of heavy elements. And this is a few units of 10⁻21 seconds. Okay. So, but in this process, there is competition between diffusion of shapes along mass asymmetry and along lambda. And in this study indicates that the amount of fusion along eta or mass asymmetry dominates the formation of the compound nucleus.
Okay,
I think this will open more longer discussion, but
yes.
I'll keep this for next some other time. Okay, thank you so much, Alexis, because obviously I have an answer for that, but thank you so much for the answer. Maybe we will have other occasions.
We keep it. We try to keep the time. So thanks, Alexis, again, and I see the next.